Okay, now that we have talked about the different states that can arise from the different combinations of orbital and spin motion of the many electron atom, we can now consider the spectra, what the spectra would look like. So the selection rule for this case is now from the electronic configuration, delta n can be anything from plus 1 or plus or minus 1 to plus or minus 2 and so on and so forth. Delta s is 0. Delta L can be 0, plus or minus 1. So this is capital S and capital L. That's the resultant. Remember, we are talking about many electron atoms. However, the small l can only be plus or minus 1, regardless of this. Delta J can be 0, plus or minus 1. There are additional rules for m sub j and m sub l. This applies in the presence of external magnetic field or external electric field. Anyway, remember that this rule comes from conservation of light, and these selection rules apply for also sounder spin coupling, where there is weak orbital spin interaction, and fails for higher orbitals, higher atoms, where there is this strong coupling between electron and spin motion. In such cases, that's in higher, not higher orbitals, please, higher atoms with higher atomic number, transition between singlet states are allowed. Remember, from JJ coupling, so those transitions are allowed. So it breaks this rule. And remember, if a rule is broken, the transition is usually not intense. Doesn't mean it doesn't happen, but it's not intense. Anyway, so let's look at alkali metal, and we can look at the broken diagram. For alkali metals, the electronic configuration is usually 1s ns. So for lithium is 1s. For sodium, that's 2s. That's the outer shell. Also for lithium it's 2s. For sodium it's 3s. So for this, L is 0 and S is up, and we have our temp symbol to be 2s out. So if we follow this selection rule, n can change by anything. S is 0, so the triplet state of the final state also has to be 2. L can be 0 or plus or minus 1, so which means we can go from S to 0 or P. But because of this restriction, we can only go from S, N 0 to P. Okay, so that gives us NP to 2S out to 2P, 1 half or 3 halves. So J can go from 0 to half to half, or plus or minus 1. It can be minus 1, so 3 halves. So this is the energy diagram. So you can go from S. So this is for lithium. So this is an absorption broken diagram. So lithium is in the 2. For lithium, the electron is in the 2s orbital. It can go to any of the p. The p state is split into, because we have J equals to half or 3 halves. Same thing there, same thing there. So this can go from here to here to here, from here to the 3p, from S to the 4p. That's because n, delta n, can take any value. So if we look at this from here, I don't have that written out here. From the P2 configuration, we can also take this transition to a triplet D state, so where L changes by 1. And you can go to the S state where L also changes by 1. One other thing that we note in this Gropian diagrams that 2s and 2p are not in the same energy level. And we talked about this. This is one of the effects of the electron and electron interaction and penetration. So the 2s orbital is lower in energy now than the 2p. The 3s is lower in energy than the 3p and the 3d. Same thing, 4s is lower in energy and the 4p and 4d. So this has been drawn a little lower in energy just to be able to explain this structure. So 2p from half goes to J equals to half. But from 3 halves you can go, so you can half to 3 halves. From 3 halves you can go to both 3 halves and 5 halves. So helium atom is 1s2, 2s2. It's a closed shell, so it's 1s0. That's the term symbol. And our transition following the selection rule can go to 1p1. The first excited state of helium is 1s2s. So this is 1s, that's the first excited state. It's close in energy to the ground state. So here we can have 1s0 and 3s1. So we can check, we've already derived this in another video. So using this selection rules as well, we can go from 1s2, same thing as this. So 1s, please see, this is 1s, not 1s. 1s, sorry. This is 1s2, this is 1s. And then we can go from 1s to s to 1s np3. So that's the electron. So electron here, 1s. Then the triplet state can go to triplet p1. Anyway, in the diagram, so this is the singlet energy levels. We can go from 1s2 to 1s2p, 1s3p, 1s4p. Then from 1s2p, we can go to 1s3d, 1s4d, or we can go to 1s3s, 1s4s, following the selection rules. And for the triplet states, we can go from 1s2s to 1s2p and 1s3p. But we notice that we don't have any transition going from the singlet to the triplet states. So again, the 1s, the 2s2p is lower, 2s is lower in energy than the 2. Then we also note that the triplet's energy levels is lower than the singlet energy levels, and we can recall this from Hund's rule that says the higher the multiplicity, the lower the energy level. Okay, so that's that about the spectra of atoms.